So let's continue from where we left off. In fact, I was just discussing with Abhinav, who's the TA for this course, and yeah, please submit all the homework files when you hard copy when you come here for the midterm exam. I think on March 9th, right? On Sunday, correct? We agreed upon. And then, what we will do is that, we will also discuss projects during that time. Okay, so how do we go about and initiate projects as part of this course? The project statements and all we will provide, and also Abhinav will help you with doing the project. Okay, through some help sessions also. Okay, as we go further. Okay, so that we will anyway come to in due course, because through those projects we will learn how all this theory that we are learning is applied in reality to automotive projects. Okay, so which is the scope of our course. Okay, all right. So in today's class, let's look at what happens with positive feedback. Okay, so that is the focus of today's class. So if you recollect, we learned how do we construct a root locus with negative feedback. In the case, suppose, very rare cases, but then if at all we encounter a case with positive feedback, we need to know what changes, right? So we already know that with positive feedback, the closed loop transfer function comes out to be g of s divided by 1 minus g of s h of s. In the case of negative feedback, kindly recall that the denominator was 1 plus g of s h of s, right? So consequently, the closed loop characteristic equation becomes 1 minus g of s h of s is equal to 0. If we rearrange this, g of s h of s becomes 1. Okay. The point is any value of s, right, which satisfies the open loop transfer function to be equal to 1, right, is a closed loop pole. Okay. So as opposed to minus 1 with negative feedback. So once again, this gives rise to two conditions, right? The magnitude condition remains the same. That is, the magnitude of g of s h of s should be 1. But now the phase condition changes because if you look at the complex plane, right? The point plus 1, if I draw a vector from the origin to the point plus 1, the angle is 0 degrees, right? Or I can take it to be a multiple of 360 degrees, okay, depending on how we perceive. So now it becomes an even multiple of pi or even multiple of 180 degrees, right? So that's how we should interpret this particular angle or phase condition. Okay, so now please note that any value of s which satisfies the open loop transfer function magnitude being equal to 1 and the phase of the open loop transfer function being an even multiple of 180 degrees is a closed loop pole. Okay, so we go through the same process as before. Now let's figure out which step get changed due to this. So let's look at this document and then let's brainstorm, right? Which steps will now change. So of course the open loop transfer function still remains the same, right? 1 plus k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn, and k is a positive parameter. Only thing which changes it is the closed loop characteristic equation becomes 1 minus k times rather than 1 plus k times. Okay, so let's brainstorm what changes. So do you think will the first step change as indicated here?
No, sir. Second step only.
So yes. So please note that the main difference with positive feedback as opposed to negative feedback was a change in the angle condition. So whichever step uses the angle condition would now change. The first step, there is no application to the angle condition, right? So it will remain the same. And as Prem mentioned, the second step will change because now with negative feedback, we took a test point and we counted the number of real open loop poles and real open loop zeros to the right of the test point. If that number were odd, because odd came from odd multiple of pi, right, in our angle condition. the test point lies on the root locus. But now with negative feedback, step number 2 changes. So now in the same document on the second page, we would have listed what are all the steps that change with positive feedback, right? Now with positive feedback, the closed loop characteristic equation is 1 minus k times s plus z1 all the way till s plus zn divided by s plus p1 all the way to s plus pn equals 0. So first step remains the same, but the second step, that condition odd becomes even. Okay, so even includes 0. Okay, so if the number of real open loop poles and real open loop zeros to the right of a test point is 0, 2, 4, 6, 8 and all, that test point, that region lies on the root locus. So I hope it's clear how step 2 changed. Okay, so the word odd becomes even. All right, everything else remains the same. Now step 3, will it change? Yes, because step 3 deals with asymptotes, and obviously, like the angle made by the asymptote was derived from the angle condition, right? So previously with negative feedback, the formula for the angle of the asymptote was plus or minus 180 degrees times 2k plus 1 by n minus 1. So the numerator 180 degrees times 2k plus 1 was reflective of the odd multiple of 180 degrees. Now it becomes an even multiple of 180 degrees or a multiple of 360 degrees, right? As displayed here. Okay, so that is how step 3 changes. The point of intersection remains the same. Okay, that formula remains the same. Now step 4. What was step 4 before, if you recall? It was about
finding a dash and b dash, sir. Like finding the k value.
Yeah, the breakaway break-in point, right? So yeah, we use that a prime and b prime and so on. Correct question, right? So this step remains the same, but the only difference is that now instead of 1 plus k times a by s by b by s, it becomes 1 minus k times a by s by b by s, right? So, but the equation b prime s as minus a b times a prime s equal to 0, that remains the same for finding potential breakaway break-in points. Okay, so that formula remains the same. Okay, there is no change in that. The only thing was that the closed loop characteristic equation now becomes 1 minus k times a of s divided by b of s equal to 0. Okay, so that is the change which happens. Okay, so I hope the change brought about in step 4 is clear. Okay, so step 5 changes. Of course, we need to determine the angle of departure and angle of arrival, right? So previously, when we looked at the angle of departure and angle of arrival, we had 180 degrees coming in, right? That is because the angle condition involved an odd multiple of 180 degrees. Now with positive feedback, you and I need to look at even multiples of 180 degrees. So we have replaced 180 degrees with 0 degrees, right? Of course, one can also put 360 degrees or any multiple of 360 degrees, okay, in this formula. That's okay, right? Step 6 is about points where the root locus will cross the imaginary axis. That once again remains the same. Okay, you and I need to substitute s equals j omega in the closed loop characteristic equation and find the potential solutions, right? Which will satisfy the fact that k should be positive. Okay, so step 6 in principle remains the same. So I hope it's clear how the steps change for systems with positive feedback. Okay, so let us apply it to the same example, and then we will discuss. Okay, if there are questions. So let's do an example. Okay, so what we are doing is that we are going to choose the same open loop transfer function, right, as before. If you recall, we constructed the root locus for this open loop transfer function with negative feedback and the case where k is positive. Now we are going to construct the root locus with positive feedback. Okay, so let's run through the steps. So if we consider first step, the open loop poles are at 0 and -4. Open loop zeros are nil. So once again, we have the two open loop poles at -4 and 0, and that's where we have two branches starting off, right? When we have k to be 0, k increasing from 0. Now step 2, once again there are three regions, right? We need to figure out the number of or the regions of the real axis on the root locus. locus. So we have three regions: minus infinity to minus 4, minus 4 to 0, and 0 to infinity. So let's take test points in each of these regions. When we take the test point between minus infinity to minus 4, we look to the right, right? So how many real open loop poles and real open loop zeros do we count to the right of this test point?
Two numbers, sir.
It is 2, right? So one is at minus 4 and one is at 0, right? So that's an even number. So we can count two real open loop poles and real open loop zeros. Of course, here there are no open loop zeros, but the total sum is 2. So as a result, minus infinity to 4, minus 4 is now on the root locus. And then if we take a test point ST2 between minus 4 and 0 and look to the right, how many real open loop poles and real open loop zeros can we count?
One.
It is only one, because there is only one at 0. So consequently, now this region is not part of the root locus, okay, with positive feedback. Then we take a test point ST3, which is on the region 0 to infinity. We count the number of real open loop poles and real open loop zeros to the right. That number is 0. So consequently, 0 to infinity is now on the root locus. So we can observe that with positive feedback, you and I get the complement of what we got with negative feedback, right? As far as regions of the real axis lying as part of the root locus. So, okay. So I think, essentially, it comes in, right? So I hope, it's clear, right? What change comes about with positive feedback. Okay. Yeah. All right. Now, what can we interpret from the, if we interpret this particular thing, we can immediately see that the branch from minus 4 will now move to the right, move to the left, okay, because the region minus infinity to minus 4 is part of the root locus, right? So I hope that change is clear. And then the branch from 0 will move to the right, okay, because 0 to infinity is now part of the root locus. So once again, we can observe a clear difference in the root locus, right? So previously, when we did it negative feedback, the branch starting from minus 4 moved to the right. Now it is moving to the left because of this observation. And the branch starting from the origin now moves towards the right instead of left. Okay, so these are the two changes that come. Okay. I hope it's clear. All right. Any questions before we proceed to step 3? All right. Okay. So step 3 is once again, essentially about calculating the asymptotes, right? So how do we calculate the asymptotes? So once again, now the condition angle made by the asymptotes is plus or minus 360 degrees by n minus m. N minus m is 2. Immediately we get, when we substitute it here, we get the angle to be 0 degrees and 180 degrees. That means it's along the positive real axis and the negative real axis. Okay, so that's what we have. So the point of intersection of the asymptote, the formula is the same, right? Sum of the open loop poles minus sum of the open loop zeros divided by n minus m. Okay, so the point of intersection comes to be minus 2. So now one may wonder, what is this? What are these two asymptotes, right? We have figured out that the two asymptotes should be at an angle of 0 degrees and 180 degrees with the positive real axis, but they should also intersect at minus 2, right? So then, what we can immediately interpret is that it is actually the positive real axis and the negative real axis which are the two asymptotes, okay, in this particular case, because there cannot be any other choice, right? We cannot have any other line in the complex plane which makes an angle of 0 degrees and 180 degrees, which also intersects at minus 2 on the real axis. Okay, the only choice by elimination is the positive real axis and the negative real axis themselves. Okay, so I hope this conclusion on asymptotes becomes clear. Okay, so I think we are just moving step by step. All right. Okay. Now we go for step 4, right? So please note, A of S is still 1, B of s is still s squared by plus 4s. A prime s is 0, B prime s is 0. Sorry, B prime s is 2s plus 4. If we solve this equation B prime A minus A prime B equals 0, we still get s equals minus 2, right? But then you notice that I have put a cross mark against s equals minus 2. While with negative feedback, we took s equals minus 2 as a breakaway point. You know what happened here? Now, please remember that the closed loop characteristic equation is of the form 1 minus A of s, k times A of s by B of s. Okay, so previously it was 1 plus k times A of s divided by B of s, right? Why? Because we have positive feedback. In positive feedback, the closed loop characteristic equation is 1 minus g of s h of s equals 0. Okay, so that's what we have. So consequently, if you and I want to solve for k, we get b of s by a of s. Previously, we had minus a b of s by a of s. Now, if we substitute and use this equation and try to calculate what happens at minus 2, we get the value of k to be minus 4, which is negative. So there is no way this potential solution is a breakaway point because we need k to be greater than 0, right? And that can also be interpreted from the step 2, right? Because if the breakaway point is minus 2, please note the breakaway point must be also on the root locus, right? But we have already concluded that minus 4 to 0 is not on the root locus, right? So through multiple mechanisms, we can eliminate that. There is no breakaway point in this particular case. So I hope it's clear, right? So the best way to figure out is what we have done here, right? You calculate solution of this equation and then find out the value of k from the closed loop characteristic equation corresponding to the solutions of this equation and verify whether we are getting k to be positive, okay, which is our condition, right? As far as the starting point of the root locus is concerned. Okay, so if k is negative, that means it's a fictitious solution. So there is no breakaway or breaking point in reality at that solution. Okay, so that is step 4. I hope it's clear how we got this. So once again, please note that steps are all similar. There are subtle differences. Okay, wherever you have an angle condition, you need to change the angle, and wherever we had the closed loop characteristic equation, the plus becomes minus. Okay, all right. So that's what happens. Now step 5 does not apply here. Okay. Step 6. Once again, we go and look at the closed loop characteristic equation. Once again, here. By the way, why does step 5 does not apply? Let's recap quickly to make sure all of us remember. Why does step 5 not apply here in this problem? What was step 5?
Minus. So the angle of departure or arrival, right? So for that reason, it will not be applicable.
So step 5 is calculating angle of departure from complex open loop poles tables at complex open loop zeros. But we do not have complex open loop poles or complex open loop zeros in this problem.
Yes.
So that's it is right. It is not correct.
Yeah.
Okay. All right. So now we go to step 6. It is determining the crossover point. For that, you and I need to work with the closed loop characteristic equation. The closed loop characteristic equation is 1 minus g of s h of s equals 0. So that is why we write 1 minus k divided by s squared plus 4s equals 0. So if we process, we get s squared plus 4s minus k equals 0. We substitute s equals j omega here. Once again, we get two equations by separating the real part and the imaginary part. From the second equation, we get omega to be 0. If we substitute omega is 0 and the first equation, we get k to be 0. That means that, like before, like there is no crossover point other than what starts at the open loop pole at the origin, right? When k is 0, there is a branch starting at the open loop pole at the origin. That's the only crossover point. Okay, that's it. All right. So now, if we plot the root locus, what happens is the following. In this particular case, after having done all the steps, it becomes quite straightforward. We have one open loop pole at 0, one open loop pole at minus 4, one branch starts from minus 4, one branch starts from 0, and one branch goes along the negative real axis as k tends to infinity. One branch goes along the positive real axis as k tends to infinity. That's it. This is the root locus, okay, with for the same open loop transfer function, but with positive feedback. Now, at first glance, it may look very simple. Yes, of course, it was a simple construction. By elimination, we could argue many steps. We reasoned out the way the root locus appears by arguments. But then we immediately observe that we have a problem, right? With positive feedback, is the closed loop system stable for any positive value of k?
No, sir.
No, right? Why? Because we have one branch always in the right of complex plane, right? For k greater than 0. So that means with positive feedback, we cannot stabilize that open loop system, right? That you and I consider in this particular example. Okay, and that can be also readily figured out by considering the closed loop characteristic equation, which is s squared plus 4s minus k equals 0, right? We recollect what was the necessary and sufficient condition for a second order polynomial to be Hurwitz, right? What was that? We discussed even yesterday.
The
Yes.
coefficients are positive and non-zero.
Non-zero and positive.
All quotient must be non-zero and of the same sign.
Same sign. Yes.
Yes.
Same sign.
So all three coefficients can be positive or all three
Or
coefficients can be negative. So in this particular case, s squared coefficient is +1. The coefficient of s is +4. So obviously the constant term also should be positive. So if the constant term is positive, minus k should be positive. That means k should be negative. But then you and I have started with the condition that k is greater than 0. So there is a conflict, right? So we can clearly observe that there is no way, we can stabilize the closed loop system with positive feedback and positive. I hope this example.
Understood, sir. Yeah.
Right?
So just one point. Am I audible?
Yes, please. Yes, please.
Sir, we had a doubt in step number. 1 second. I will just scroll back into
6 on.
step number 2, right? Sir, we had a doubt that in this case we are limiting to one region in between the 2 points, right? For example, either side of -4, which is on towards minus infinity and one is towards 0.
Region 1 and region.
Region 1 and 2.
So what is the question, Prem?
Sir, maybe you can draw it again. I'll ask again maybe.
So see, I'm drawing a fresh diagram. Okay, only
Yeah.
So see, step 2 applies to figure out, or step 2 is used to figure out what portion of the real axis lies on the root locus. For that, what you do is that you plot all the open loop poles and open loop zeros on the real axis. And they divide the real axis into different regions. Okay, so this is region number 1, which is between minus infinity to -4. Region number 2 is minus infinity to 0. Region number 3 is between 0 to infinity. These 3 regions remain the same whether it's negative feedback or positive feedback. Okay, so but then you and I need to take a test point in each one of these regions and look to the right and count the number of real open loop poles and real open loop zeros to its right. In this particular case, with positive feedback, if the number is even, then that region is part of the root locus. Okay, because it satisfies the angle condition. Right. So that's how you and I did do stuff. I hope it's clear, right? So,
Understood, sir. So we will always search towards the either sides only. We will never search in between the 2 poles.
no, we are also searching in between the 2 poles, right? That's region 2, -4 to 0.
Okay.
So that's why I told there are three regions, right? So in this particular case, because it splits into 3 regions. Okay, so please note that. All right.
So basically, in the negative feedback system, sir, since the angle condition is like odd one, hence we have to look at the only poles which are having like odd numbers will be the part of root locus. Otherwise, it will not be.
No. I think let me be careful, Roshan. I think we discussed this yesterday also, right? Yes, if you recollect, I'm going back now, right? Because since this question has come, please note, like when we essentially look at, things to the right. Okay, where was this?
Yes, sir.
Yeah,
Here,
step 2,
yeah.
right? Please note that, the the angle made by that vector from the test point to the open loop pole or open loop zero on the real axis will be 180 degrees if that 0 degrees if that open loop pole or let me put it the other way, like the angle made by the vector drawn from an open loop pole or open loop zero to the test point which lies to the left of it will be always 180 degrees, right? So if you want a angle condition to be odd, you want the number of real open loop poles and real open loop zeros to be odd, okay? So that's why with negative feedback, it was odd.
Yes,
With
sir, yes.
positive feedback, the angle
is a-
condition is 360 degrees, right?
Yeah.
As we interpreted, it's an even multiple of 180 degrees. Okay,
Right,
that's
sir.
why we want the number of real open loop poles and real open loop zeros to the right of the test point to be even. Okay, so I hope that clarifies this point. Okay,
Right, sir. Right, sir.
so
Right, sir.
so in this particular step, like always, you and I need to plot the open loop poles and open loop zeros and write down what are all the subregions. And then once we identify the subregions which are created, you and I take a test point in each subregion and then go to the right of that test point and count how many real open loop poles and real open loop zeros are there. Okay, so that's it. Like I hope this step is clear, right? Yeah.
Yes, sir. Yes, sir.
All right. Fine. Any other questions on the root locus construction with positive feedback?
Sir, in step number 2, we are taking 3 regions.
Oh.
Third region we can technically ignore, right? Because it, I mean, always the values are positive. I mean, RHS of the S plane. So that's not going to be stable. So we can technically ignore that point.
But no, but then we never know in generality, like because see, in this particular case, one branch always is on the positive real axis. If you have complex conjugate open loop poles and zeros, right, what will happen is that you will have, breakaway break-in points even on the positive real axis. So kindly do not neglect that. Okay, please consider that. Okay, yeah.
Okay.
Right? See, you and I are doing simple examples here. Okay, so for these simple examples, it appears as if it may not matter. But when we go to complex examples, it will matter. Okay, yeah. So we always learn theory for the general case. So kindly retain this. Okay?
So for example, the point will be on the positive real axis like +4 or something, but then we'll again search towards the left hand side and then the point will come to the LHP of the imaginary axis.
No, I didn't get it. Sorry. Can you repeat it, please? Like so. Yeah.
So just to ask the same thing that Keshav was asked, if there is a point on the real axis, like for example +4, and then I start searching, then I'll come towards the left hand side probably. That's why we still prefer to search even though it is on the RH side.
See, what happens is that, like Prem, suppose if there were poles like this, okay? So what may happen, right? I have multiple poles. I am taking a higher order system, right? I'm arbitrary drawing, okay? So there is no logic here. Please don't, look for accuracy here, but I wanted to show a point, why it's important.
Sure,
There
sure,
may be
sure.
cases where you may have this region in the positive real axis being in the root locus, there may be a breakaway point. Ultimately, these two branches may come in and then end at two open loop zeros, okay, on the negative real axis. So you don't neglect them. All I okay. Okay.
Understood.
So in the simple case that you and I have considered, it turns out that one branch is always on the positive real axis. So so essentially we are saying that it's unstable, right? But it is not always the case. That's all I am telling. Okay. So please don't.
Okay, sir. Yeah.
The general case, okay, not for specific. Right?
Thank you, sir.
Okay. Any other points? Okay. So now let's go and figure out for the complementary cases, right? So because see, you and I started off with the cases where K was positive, but what happens if K were negative? Okay. Then how do we construct the root locus with positive feedback and negative feedback? Let's look at it. Okay. So I hope it's clear because A real controller parameter can go from minus infinity to plus infinity, right? Who told it should always be positive, right? So it's not necessary, correct? So you and I, as we discussed, should always plan for the general case, okay, not for the specific case. So given that, how do we, plan for this particular, case where k is less than 0, right? So if we consider the case where k is less than 0, right? With negative feedback. So let's first consider what happened. Yeah, we have negative feedback with k being negative. Then what happens is that we have the closed loop characteristic equation with negative feedback being 1 plus k times s plus z1 through zm divided by s plus p1 all the way till s plus pn, okay, equal to 0. Now, what we do is that we do a very simple, definition of or change of parameters. We define a parameter k hat, which is minus k. So then if I substitute for k, k becomes equal to minus k hat. But what is the implication? Then this equation becomes 1 minus k hat times s plus z1 all the way till s plus zn divided by s plus p1 all the way till s plus pn. But now k hat is positive. Okay. So the step of constructing root locus with negative feedback and negative k becomes equivalent to constructing the root locus for positive feedback with a positive k hat. So what you and I do is that we follow the steps that we learned today, right? For positive feedback with positive k hat, construct the root locus, and the root locus will be what you and I can obtain for negative feedback with negative k. I hope this subtle but powerful variable change is clear to all of us. All right. Okay. Similarly, if we look at what happens with positive feedback with negative k, I hope by now we would have figured out what we will do, right? With positive feedback, the closed loop characteristic equation becomes 1 minus k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn equal to 0. So what do? We do this similar thing, right? Now we define k hat to be minus k. K becomes equal to minus k hat. This now becomes 1 plus k hat times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn equal to 0 and k hat being equal to 0. So now this looks as if it is a positive or a negative feedback system with positive k hat. So you and I go and apply the corresponding steps for negative feedback, right, with positive k hat, and then we go from there, right? So I hope this is clear, right? So let me explain this grid once again so that things will become clear. So let us say we call as set 1 or first set of steps all the steps that we learned till yesterday's class. That is, we had negative feedback with a positive parameter k. Like let's say we call that as a first step of set of steps, right? So that is under negative feedback and positive k. We already learned it. Then today's class we learned positive feedback and positive k. Let's call this as second set of steps. Now, as we learned just now, if we have negative feedback with negative k, what we do is that we substitute k hat to be minus k, and we follow the second set of steps for an equivalent positive feedback system with positive k hat. Okay, we construct the root locus. Then if you have positive feedback with negative k, we once again substitute k hat to be minus k. We follow the first set of steps, right? And then with positive k hat. Okay, so this way, you and I can construct the root locus for either negative feedback or positive feedback and positive k and negative k. I hope this set of steps, what we do with negative k becomes clear to all of us, right? I hope it's clear to all, right? Any questions on this?
Sir, the steps are clear. One thing I want to ask you that let us take the example of negative feedback with negative gain in that sense. What are the practical example that we can just correlate this?
So sometimes, see, the point is your closed loop transfer function itself may come such that, like you may only have negative values of controller gains, which may give stability. Okay. So it depends on the problem construction, Roshan, right? So by and large, once again, the keyword is by and large that, you will have negative feedback, and mostly controller parameters will turn out to be positive in practical applications. But you and I should be prepared for every situation, right? In theory, right? That is always the purpose of any theoretical discussion, right? Sometimes the problem definition may be such that we may have stability coming through only the case where the controller parameter is negative. So we should be essentially having a plan for that. Okay, that's why we are learning. Okay, so if you ask me, it's very likely that we will be focusing first on the first cell in this grid by and large. Okay, but we should also know, suppose if we have a negative feedback system and the gain happens to be negative, how should I approach that problem? That's why we are learning these steps. Okay. Yeah.
Thank you, sir.
Okay. So yeah, I hope these steps are clear. So now this brings us to homework number 3. I hope this is homework number 3, if I recall correctly, right? So what I want you to do is that, like, there are 2 open loop transfer functions that are being given. So I want you to plot the root locus, right? Of course, with negative feedback and positive key. That means it's the step 1. Okay, first set of steps, right? So please follow all the steps. What I want you to do is that, do the problem, with hand, and show all the 6 steps. Okay, and then plot the root locus. All right. Okay. So I hope homework number 3 is clear, right? In the first step, we have the open loop transfer function to be k times s plus 2 divided by s times s minus 2. So the open loop poles are at 0 and 2, and open loop 0 at minus 2. Okay, so you need to plot the root locus there. Okay, so and in the second problem, the open loop transfer function is k times s minus 1 divided by s squared plus 2s plus 2. There's an open loop 0 at 1, and then you're going to have complex conjugate roots on the open loop poles at minus 1 plus or minus 0. Okay, so you will see that you need to also apply step 5, okay, which is calculating angle of departure and angle of arrival, right? That step also will come into play in second problem. So these 2 problems will give you a good overview of root locus and practice also, right, on how to plot the root locus. Okay, fine. So please do this as homework number 3, and once again, you can submit the hard copy when you come in person, okay, for that midterm exam.
Sure, sir.
Any questions on this homework problem?
Sir, on the
Yes,
previous discussions that we've had, here we are assuming even k is either positive or negative. How do we attribute in real world conditions if at all we construct a controller?
So typically what happens is that when we do stability analysis, right, you and I will be able to find regions of the controller gains which will give us stability. Okay, so we may get some ranges, some conditions that they should be positive or negative, or between -3 to infinity and so on, right? So that will give us a handle on what should be the condition, right, under which we should plot the root. Okay, yeah. So that comes from stability analysis. Okay, so what we have figured out here is that irrespective of the sign of k, what steps to do. Okay, that's what we have learned. All right, so that is the focus here. So when you do case studies and all, things will become clear to you. All right.
Yeah, fine. So one more question. If you can go to yesterday's session.
Yes, please.
We were mapping Yeah, how are we deriving here, sir? How are we deriving this graph? We are considering the region of focus as -1 to -2, right? Why it can't be -2 to -4? Because that's also falling within the stability and the performance requirements.
Okay. So once again, if you're asking me, you are saying, hey, look, between 0 and this k equals 4, one branch is always within the open trapezoid, right? But
Yeah.
please remember, for performance, we need all closed loop poles to be in the open trapezoid, not one. Okay, yeah. See, just like for stability, we need all closed loop poles to be in the left of complex plane. For performance also, all closed loop poles should be within this open trapezoid. Please note, between 0 and 4, one branch is outside this open trapezoid, right? That is why, we are starting from k equals 3. Okay, I hope it's clear, right?
So let me rephrase my question. There is an open trapezoid you are getting. If you draw a line from -4 to the intersection points, even then we are getting a open loop trapezoid, right, sir?
No. I think maybe let me articulate it by redrawing this entire thing. Okay, so since this question has come, there are two things here, right? So one thing is that let me go step by step. Okay, so see, there was this open trapezoid which came due to the performance specification. Okay, so this before we started the root locus problem. Is it clear? Is it understood? So this point was at -1. Okay.
Yeah.
Yes, sir.
Plus 53.7. So
Yes.
this has no relationship to the root locus that we drew yesterday. Okay, this is the open trapezoid is the region where if the closed loop poles lie, we will also have performance specifications to be satisfied. Is that clear? Yeah. Now, in the specific problem, see, unfortunately, I'm unable to change the color of this line, because if I change it, it will change everywhere. Okay, so now in the specific problem, we had one branch starting like this, one branch starting like this. Both branches had a breakaway point at -2, and then they went here. Now, let's say this we call as branch 1, this we call as branch 2. The question is, under what range of k do both branches 1 and 2 lie within the open trapezoid? Because once again, for performance, we need all the closed loop poles to lie in the open trapezoid. Okay, so that is why we ascertained what was the value of k at -1, because one branch is this branch 2 enters the open trapezoid only at this point, right? Before that, it didn't. It was outside the open trapezoid, which correlated to the performance criteria. Okay, so that is why we started from here. So although I understand your point, saying that look, in branch 1, it always lies within the open trapezoid between -4 and -2, right? That is one closed loop pole. What about the other closed loop pole? Okay, we need to consider both. That is the reason. Okay.
Yeah. Thank you.
So, sir, the final output, can you just share the area where we will actually search? That
It is going to be, that's what we have shared in blue here, right? In K.
Yeah.
3 to 11.45. Okay, 3 is here. 11.45 is this point. Okay, when we calculate.
Yeah.
Okay.
So the open trapezoid has got limited by the asymptote coming from the breakaway point.
That is on one side. On the other side, on the lower bound of k is also constrained or determined because of the fact that only beyond the lower bound of 3 will both branches come in the open trapezoid. See, both branches should lie open. Okay, I should say all in general, right? Should lie in the open trapezoid. See, it is like this. See, for stability, what was the condition? All branches should be in the left of complex plane, right? See, will I accept some case like this where, let us say, I have, to give you an analogy, to all of it, let us say I have another root locus, right? Where I had at -4 and +1, okay? So it intersects at some point, and then it goes like asymptote, right? Can I say it is stable for all k greater than 0? No. Why? Because for k till, let's say, some 3, or let me not choose the same value, let's say some 5, we will see that this branch will always be in the left of complex plane. But what about this branch? Okay, it is outside, right? The left of complex plane. So it is unstable, right? Similarly, for performance, we need all the branches to be in the open trapezoid. When does that happen? Only when k is greater than 3. Okay, so I hope it's clear. Okay.
Clear, sir. Just one. I'm sorry to ask this again. Very sorry again, but asking so that we don't forget it. How did we arrive at -1 again?
-1 because settling time condition frame. Settling time was 4 by zeta omega n.
Yeah.
That should be less than 4, right? So
Yeah.
zeta omega n should be greater than 1, which implies minus zeta omega n should be less than -1. So what was minus zeta omega n? Minus zeta omega n was the real part of the
Okay.
pole. So you draw a vertical line passing from -1. So this condition means that all poles which lie to the left of the -1 point will satisfy the settling time. Okay, that is what we discussed, right? That's how you convert the settling time criteria to this subregion in the left of point.
Clear, sir. Thank you. Thanks a lot.
Similarly, the peak overshoot condition gets converted to a cone.
Yeah, the angle.
Right?
Yeah. Beta.
So whichever is within this is satisfying peak overshoot. I need to satisfy both, because what is the problem? We have asked settling time and the peak overshoot. That is why we consider this open trapezoid.
Sir, what if there are no pre-requisites?
Let me complete another case frame, then kindly ask your question. I'm sure that may also partly answer your query. Suppose in the problem statement itself, right, when we started off, let us say, like the problem statement itself is that instead of 2 performance requirements, I have only settling time performance requirement. How will this problem change? Then
the cone will vanish.
We will have the cone will vanish. So I will have only the vertical line. So the feasible region for performance will be 3 to infinity as far as k is concerned. Right? I hope that's how it will become. Okay, depending on how the performance metrics are specified. On the other hand, if I have only the peak overshoot as my performance metric, not settling time, what will happen? The feasible range of k will be 0 to 11.45. Okay, so that's how things will be. I hope that these examples are.
Yes, sir. So as I keep on adding the constraints, I'll be able to narrow down. But if I have an initial condition which is very minimal information, I'll have to search for a larger space and then.
Obviously, right? So if you put more constraints, you will get a narrower range of feasible region in which you need to tune. That is the engineering decision we need to take, right? See, let us say if this were the transfer function of a steering motor, right? You and I need to take. If I control the steering motor, do I want settling time of 4 seconds and a peak overshoot of 10%, or one of the two, or none at all? Okay, that is something an engineer should decide, right? What I am conveying is that suppose we have taken the decision, what tool to use to get feasible regions, okay, of the close to of the controller. Okay.
Thank you, sir.
Yeah. Okay. Any questions?
Sir, for midterm class number 16 up to 16 is the portion, sir.
I'm sorry, what is it?
For midterm exam, what is the portion, sir? Up to 16th class video? Or
so when is our midterm?
9th, sir, 9th.
March 1. What is today?
Today is 18th, sir.
No problem. Okay, we will take whatever we have learned till today as the syllabus for this. Okay.
Right, sir. Right, sir.
Because I think that will be a natural point for us to stop, because from tomorrow I will be looking at frequency response. Okay. Yeah. Which is also an important topic. See, we are going to do projects in automotive domain using all these tools. Okay. So once again, I'm reiterating. Kindly do not think, oh, okay, why is this guy boring us with some generic theory and so on, right? So no, right? So the way the theory concepts have been taken is that like in the second half of this course, once we are done with bulk of the lectures, Abhinav will help you with the projects from automotive domain, which we have done in a research group and which is being implemented in practice. Okay, so you will be able to see the application of these things too, really. Okay, that is when we are in control of automotive system, right? Otherwise, I could have turned with control theory, right? So.
Thank you so much, sir. It is very like meaningful in that sense. Thank you.
Okay, welcome. So I think we will continue from this frequency response tomorrow. So let's agree that for the midterm we will have till this point.
Right, sir.
Right? Okay. And attendance, is everyone present today?
Yes, sir. Yes, sir. Everyone is present, sir, today.
Okay, everyone is present. Okay, so I'll mark everyone as present.
Right,
So then we will meet tomorrow and continue from there. Okay, thank you very much.
Thank you, sir. Thank you very much.
All, thank
Thank
you.
you, sir.
Bye.